go ahead and get started. So welcome everybody. This is we have the honor of being our first visual computing seminar speaker of the new fall semester. So yeah, to kick things off the semester, we're very happy to have Ticha joining us all the way up from Boston, up at MIT, where she works in the HCI Engineering Group with Stephanie Muller. Has also done some collaborations with Mackenzie Leak, who's been here before and is a friend of the department. Yeah, so really excited to hear. I've seen Ticha speak before at, I think it was NESG, up at MIT. She does some really cool work on, well, I like this way of phrasing it, engineering expressive technologies, but designing, physical and computational artifacts that help people be creative. And I'm excited to hear what she has to say today. So welcome, Ticha.
Great. Thanks for the introduction. So again, thank you for having me. I'm so happy to be the very first speaker of this semester. Hopefully I'm putting things off to a good start. Again, I'm Ticha. I'm a PhD candidate at MIT in the HCI Engineering Group. I'm primarily a human-computer interaction researcher, but graphics and visual computing continue to play really important roles in how I develop my research projects. So I'm really glad to be in this visual computing seminar. So today I'm excited to talk to you about my research on building expressive technologies. So I guess before I talk about how I build expressive technologies, it might be useful for me to define what I mean by an expressive tool. And my definition is that the more expressive a tool is, the more that you can make with it. And kind of to follow up on that, I think people are only as expressive as what their tools allow them to do. And one of my favorite sort of foundational HCI research papers is one called The Past, Present, and Future of User Interface Software Tools. And this was written by Brad Meyer, Scott Hudson, and Randy Pouch. And if you've read this paper before, you might be familiar with this concept of the expressive ceiling. So the idea that people are as expressive with what their tools allow them to do kind of ties into this concept of okay, the expressive ceiling is kind of what is the most that you can do with a tool. So humans have come a long way in sort of raising the expressive ceiling of their creative tools. So I remember the very first painting program that I used was MS Paint for Windows 98. And maybe some of you even use Mac Paint from 1984. But I feel like, the more I give this talk, the fewer people actually use that. But yeah, and since then, we hit many milestones in the domain of this is specifically image creation and painting. So for example, we have Photoshop, which introduced layers to image making back in 1995. And then we have Procreate, which is this iPad app released in 2011. And that kind of set the standard for mobile painting. So you don't have to have, this bulky desktop anymore. You can just kind of take your iPad on the go and make these very, very detailed artifacts. And now we even have these really advanced AI models that can generate entire images from text. And these advancements also apply to the tools that we use to physically build things. So in addition to expressive software, we now have a lot of really expressive hardware and fabrication machines that enable us to build hard and soft things, small and large things, things that you can fit into and things that fit you. But I argue that the expressive ceiling of these machines that we use to make all these things is not quite as high as what we can make with computers. So, to demonstrate what I mean by this, I want to see a show of hands. How many of you have studied animation or have a degree in animation? Oh, dang, okay, that's, okay, great. And how many of you have used a computer to make literally anything that animates, like anything that moves. Great, okay, yeah, so things like animations and interactions are like really easy to prototype in digital space. So you don't need special training or even special tools to make them. So for example, if I wanted to make an animation of a fish that dissolves into bones when I click on it, that was really easy. I just did this in PowerPoint. Awesome. So I don't know, have any of you tried printing an animation? Okay, let's see what happens if I try to print that fish that I just made. Yeah, so it turns out that interaction is really not trivial to reproduce in real life. And that brings me to the core of my PhD research, which is how do we build systems that can make physical materials as expressive as digital media? So I call this dynamic media, which are artifacts that have the ability to sort of change their appearance when you interact with them. So a critical design goal that I have in developing dynamic media is to make these effects possible with purely analog materials. So if you saw from like this video, there's no electronics here, nothing. Like this is like just like purely materials based. But of course, we could just trivially make dynamic media by putting little screens on everything. So, why would we bother with analog materials to begin with? Well, at the end of the day, a lot of what we interact with on a daily basis is made from analog materials. So the door that you use to enter the room, the chair that you're sitting in right now, like just this water bottle, this podium, and our clothing. So philosophically, I don't think that it's just about making physical materials, behave exactly like digital media. What I'm more interested in is kind of expanding the expressiveness of physical material to have some properties that we might find in digital media, but we also want to sort of preserve the unique characteristics of the physical materials themselves. And this is kind of a theme that I'm going to come back to near the end of my talk. So in my research, I create dynamic media with two kinds of design systems. And I use two kinds of these approaches. The first approach is more materials forward, and the second approach is more perception forward. So material forward approaches rely on using special materials that can change states in response to external stimuli. But in the absence of these special materials, we can try perception forward techniques that can trick our brains into thinking that inherently sort of static materials can actually behave in dynamic ways. And today I will be talking about 3 different projects that I published in my PhD that apply these methods to sort of varying degrees. So the first project is called thermochromorph. And thermochromorph is what I call a fully materials forward approach that uses thermochromic inks that change color in response to temperature. And this was presented at SIGGRAPH Asia in the art papers track back in 2024. And what's really interesting is that it turns out that we can just apply off-the-shelf thermochromic inks to conventional imaging and printmaking processes to create these full-color dynamic images. So as you can see, what's happening here is that I'm putting the prints on this hot plate, and it can transition from one image to a completely different one. And kind of the way that this works under the hood is that we're using thermochromic inks with complementary color changing properties. So we have like some inks that transition from color to clear when they heat up, and others that go from clear to color at the same activation temperature. And when we print these inks on top of each other, we can achieve what looks like a color to color transition. And this process is also fully reversible. So when the print cools down, it will return to its original state. So the example that I showed in the previous slide is essentially just a single pixel, but most images are more than 1 pixel wide. So to support multicolor image-to-image transitions, we need a process that's more scalable because we don't want to be stuck accounting for possibly exponentially many transitions because each image is made up of many colors. So to address this challenge, we leverage the CMYK imaging process. So this is a very widely used technique in the printing industry, which you may be familiar with. So CMYK represents multicolored images using just 4 channels: cyan, magenta, yellow, and black. And first, we define what we want our so-called hot and cold images to be. So the cold image is what's visible at the room temperature, and the hot image is the image visible at the activation temperature. And for each of these images, we decompose them into their constituent CMYK layers. And sort of each layer represents one printing matrix. And a printing matrix is like a stamp where the raised portions of the block hold ink, and the recessed areas do not. And the hot image uses CMYK matrices that hold clear to color inks, and the cold image uses CMYK matrices that hold color to clear inks. And I think what's most powerful about this representation is that regardless of how many colors there are in each image, you will only need at most 8 printing blocks. You will never need more. And to sort of tie all this together, we additionally provide this imaging software that handles the process of making printing matrices for desired image-to-image transitions that visualizes how the print should look. So we can use the outputs of our software. Did you have a question?
Sorry, what do you mean by matrices? Did you mean the raster?
So the matrices are just the printing blocks. Yeah, we call them like matrices, but they're just like the blocks that are used for printing. You can also call them stamps. Yeah,
Thanks.
Great. And yeah, so using the outputs of our software, we can engrave our printing matrices or printing stamps with a laser cutter. And the black areas in these images represent the recessed portions, and the white areas are the ones that are raised. So yeah, the printing process is really just stamping the blocks one by one, layer by layer, starting with printing the hot image and then the cold image. And you can see the process of building out the image. So I think what's really encouraging about this process is that it's actually not harder to learn than regular printmaking. So to sort of validate our process, we brought in 3 artists for a group printmaking workshop, and then we showed them how to use our system to create their own color changing prints that they designed themselves. And this is the set of prints that they made. So hopefully you can kind of see it here, it might be a little fuzzy, but what I really like about the prints is just how stylistically diverse they are. So you can kind of see how they were able to capture both geometric and organic forms. But I think what's most exciting is that the process to get there is approachable. So even though only one person in the workshop had sort of prior formal printmaking experience, everyone was able to successfully make the images. So we were able to, do something that's usually out of reach for people, and allow them to make these new things that they couldn't make before.
Next question, how do you actually make the printing matrices, like physically build them? How does that work?
Physically build the
Yeah,
printing.
stamps. Yeah.
You mean like besides the laser cutting, or?
Oh, that's maybe I just missed.
Yeah.
Okay.
So there is like, sorry if I like kind of breeze through that.
Yeah.
So yeah, in this slide, yeah, it's showing like basically our software. Let me just play it out. Yeah, our software outputs the left images.
Yeah.
And that's just the images that is served as input to the laser cutter, and it analyzes that and
Gotcha.
produces it. But you could also, if you didn't want to kind of completely do it in an automated way, you could also just carve out the printing matrices yourself and use these as templates for carving. Yeah. And yeah, so I think that what we learned here was that it lowers the barrier to working with these materials, but it also leaves a lot of room for individual style and experimentation. All right, so thermopromorph uses a color changing material that is sort of specially engineered to behave dynamically. And this next project, Polygons, uses a material that isn't sort of explicitly designed for color change, but rather the color changing aspect is a side effect of the material's optical properties. So I kind of argue that it's in between the materials forward and perception forward approaches, even though it is itself kind of a special material. So polygons is a system for designing and fabricating these mosaic-like structures that change color based on polarized light. And this project is just really special to me because of how it bridges knowledge from arts and physics and computation. So conventional imaging techniques, like what we saw with thermochromorph, rely on sort of applying pigments and dyes to surfaces to create artistic imagery. But in the 1960s, some artists explored this new medium for painting, which is light. So in particular, artists discovered that we have these materials with special properties that allowed them to change their appearance based on how polarized light passes through them. And these materials are called birefringent materials. And the artwork made from these materials is known as polarized light mosaics. So what's really nice is that in addition to having these unique optical properties, most birefringent materials are very inexpensive and easy to find. So the mosaic on the left was made with packaging tape, while the one on the right was made with cellophane film, which is something that you can get from sort of gift stores. I think it's commonly used for gift wrapping. So you can make a mosaic yourself by sandwiching pieces of the birefringent material between two polarizers. So it's like if you've ever had a pair of sunglasses, a lot of sunglasses have the polarizing film. So you can just kind of like take apart your sunglasses and make one of these mosaics today with some tape. And I think what's most compelling about polarized light mosaics is kind of the ease with which you can create these color changing effects. So as you remember from thermochromorph, it's like, okay, these inks are all heat activated, so you would still need like a heat source to change the images. This is like even easier. Like you don't need anything at all. You just need to kind of turn it, and then you're able to create these dynamic images. So all of these color changing effects can be achieved by planar rotations. Yes.
How many colors do you have? Is it just like two configurations and two rotations, or how does it work? Like
Yeah. So I'm going to go into more details
Okay.
later, but at least like the ones that have more, I guess, like controllable effects, like realistically, you can go from like one clear image to another image. So it's like two, but you know, in theory, there are like hundreds of different colors and like hundreds of different transitions, but like the clearest ones are kind of like 2-frame animations. Yeah, great. So for a really long time, there were no support tools for making polarized light mosaics. So they were made entirely by hand, and artists often had to resort to experimentation before they even know what colors they have access to or what effects are feasible. So in practice, you know, very few people work with this medium because of how challenging it is to master. And this video shows sort of a master polarized light mosaicist at work. Her name was Faustine Wood Comero, and she was kind of the pioneer of this art form. And even though she was like working with this medium for, I don't know, 50 years or something, each piece that she makes takes a really, really long time for her to finish. And I think that like the other interesting part is that, you know, in the world of physics, these materials are actually super well studied. So there are existing models that can predict exactly what colors you'll see based on the material properties and light orientation. So the core idea behind our system is sort of what if we can take that theoretical foundation and use it to build a computational design and fabrication process that can make this medium sort of more accessible to general users. So I'm going to kind of walk through how this all works. And to understand how this all works, I'll go through some of the working principle for these materials. So most everyday materials are what we call optically isotropic. So the speed of light is constant for every angle that it passes through the material. But birefringent materials are optically anisotropic. So the speed of light varies depending on the angle that it propagates through the material. So unlike isotropic materials, which have a single refractive index in all directions, anisotropic materials have a refractive index that varies depending on the direction of light passing through them. And the difference between this maximum and minimum refractive index is known as the birefringence. So as I mentioned before, cellophane is a popular birefringent material among polarized light mosaicists because it's very common and easy to find and cheap. So it has this useful optical property as well. So its birefringence tends to be pretty uniform across the surface. So that makes it well suited for sort of predictable and consistent color effects. All right, so I will walk through the mathematical theory behind the color changing effects you see in polarized light mosaics. So similar to how stained glass mosaics are made from disjoint pieces of glass held together by plaster, polarized light mosaics are constructed from these sort of disjoint stacks of cellophane held together by a base. So usually it's like an acrylic base or basically any base that is not is optically isotropic because you don't want it to also change colors with the mosaic, so like a neutral base. And then the mosaic is sandwiched between two polarizers. So what the polarizer does is that the polarizer filters light so that only waves vibrating in one direction pass through. And the light needs to be polarized because the birefringent materials really only create these color effects under polarized light. Otherwise, the changes are invisible. So this is why usually when you look at cellophane, it's just completely transparent. You don't see any colors. So what the first polarizer does is that it polarizes the incoming light. And what the second polarizer does is that it filters the modified light to reveal the resulting colors. And for clarity, there are two polarizers, but we'll refer to the polarizer that the viewer looks through as the analyzer, and the one at the bottom we'll refer to as the polarizer. But they're both polarizers. So I might be using like analyzer, polarizer. They're like the same thing. It's just different positions. Okay. So the emitted color of the cellophane stack depends on four factors: the thickness of the stack, the birefringence of the cellophane, the angle of the analyzer with respect to the cellophane stack, and the angle of the polarizer with respect to the cellophane stack. So using these parameters, we define this transmittance function, which tells you how much light is being transmitted at a given wavelength. And just like for some intuition behind like how this works, you note that the transmittance remains unchanged if the relative angles of the analyzer and polarizers are reversed. So that this just means that the colors look the same when the mosaic is flipped upside down. And since transmittance depends on both like the birefringence of the cellophane as well as the thickness, the equation additionally implies that two stacks of the same thickness can still have different colors, even if their birefringence values are different. Yes.
What is the little R refer to on the T?
That's like just the function that people use for transmittance, TR, transmittance. I believe this is just a convention that I guess the physics people like to use. You could get rid of the R and it's still fine, yeah. Cool. So we can use the transmittance function to compute the color values by integrating across all visible wavelengths. And these integral bounds correspond to the visible spectrum in nanometers. So again, these color values are in XYZ color space, but we can easily convert them into RGB. So just to give you like more intuition, X, Y, and Z are just constants that you can get from a lookup table. And E0 is also just like a constant radiance, which we usually assume is 1. Don't ask me why it's 1. This is just a value that I guess the physics people like using for convenience to make the math neater. So note that this equation for transmittance also assumes that the stack comprises of only one type of cellophane, where the birefringence is just constant throughout the stack. But in practice, an artist might use multiple types of cellophane in their mosaic, each with different sort of native thicknesses and birefringence values. So we can modify this transmittance equation to account for multiple types of cellophane by simply taking this sum across thicknesses and birefringence values for each sheet in the stack. So that's just all the mathematical theory behind the colors that you can expect.
Does that assume that the cellophane is a thin sheet?
Yes, well, actually, you can technically apply.
Has the seed that
Yeah, I mean, the
we
Z
have
could
two
be
different
larger.
stacks there.
Sorry.
Have like 2 different sized stacks.
Yeah, so that can still work. Like, it doesn't really matter how thick the cellophane is. It's mostly just like if you have 2 different size stacks, it might look like weirder, or it would just look unbalanced, or it makes the fabrication process a little harder. Yeah. And yeah, if we then evaluate all possible sort of linear combinations of cellophane stacks, we find that we're able to produce sort of hundreds of colors using just 5 types of cellophane. So 5 types because this is like the number of different types of cellophane that we were able to acquire. You can also just like add more sheets of cellophane and you'll be able to get a larger color gamut. So this is kind of similar to thermochromorph, where we were able to express hundreds of different color transitions with just 8 types of thermochromic ink. So with the theory covered, we can now explore a range of possible color changing effects. So the most basic mosaic uses 1 layer of cellophane sandwiched between the 2 polarizers, which results in a single colored design. And when the polarizers are aligned with the cellophane, the mosaic appears colorless, but at a 45-degree rotation, it reaches peak saturation, and this effect cycles every 90 degrees. And it's 45 degrees because if you plug in the angle values of 45 into that equation that we saw before, we find that that produces like the most saturated color. And also note that since color change is based on relative orientations, we can kind of achieve the same effect by rotating just the mosaic or rotating both polarizers together, which I think this animation is hopefully showing. Great. So the orientation of the polarizers with respect to each other also affects the appearance of the design. So colors under parallel and orthogonal polarizers are complementary to each other. So notice how the background also changes to black when the polarizers, are orthogonal to each other. And this is because orthogonal polarizers block light, while parallel polarizers allow light to pass through. Okay, so recall that the thickness of the cellophane is one factor that affects the colors you see. So if we just kind of assume that the birefringence is constant, we can create these multicolored designs by stacking multiple pieces of cellophane together and arranging them to form an image. So all the color effects that I talked about earlier worked in the same way. All right, so what if we wanted to fade 2 mosaics into each other? So since mosaics appear colorless at 0-degree rotations, and then they reach full saturation at 45-degree rotations, all we would have to do is offset 2 mosaics by 45 degrees, so that when one is fully saturated, the other is completely clear. So note that this is kind of conceptually similar to thermochromorph, where we overlay inks with opposite behaviors to create these sort of color-to-color transitions. And the very last effect that I want to talk about is masking. So a mask is just a third polarizer that is inserted between the topmost mosaic and the analyzer. And its visibility depends on its alignment relative to the analyzer. So since polarizers block light when they are orthogonal and allow light to pass through when they're parallel, when the mask is orthogonal to the analyzer, that's when it's visible. So this is actually an effect that the artist Austin Wood-Komaro uses extensively in the mosaics that she creates. Cool. So based on all of these effects, we can kind of define a sort of typology of mosaics that you can create with our systems. So our system supports these 4 mosaic constructions. The first is a single mosaic construction that has a single image, which can transition from transparent to opaque, as well as invert its color. And then the double mosaic construction has a second mosaic layer, which allows support for 2 images that can crossfade into each other. And the last 2 constructions are variants of the first 2 with just 1 additional polarizer that's used for masking. So next, I will briefly highlight some key features of our design tool. So we have this set of design templates that are based on the 4 mosaic constructions that we defined. And these templates allow users to control the complexity of their design and ensure their outputs are valid. So here we're selecting the double mosaic single mask construction. And once users select a design template, our tool loads all the default template files into the main window. And what this main window shows is sort of all the keyframes of a design. So a keyframe represents a view of the mosaic in which either of its mosaic layers is at full saturation. So I know, Adriana, you were asking about like what are the different possible effects and appearances. I guess you can consider, if you consider like each keyframe as being like, okay, the mosaic looks a little different. Like in theory, we have a maximum of 8 possible appearances for the most complex design. So this is the 8 keyframes in a single or double mosaic single mask construction. So, users can also replace the default designs with custom ones. And what our tool does is that it just takes SVG images as input. So you can import any SVG image, and the interface automatically maps each color to its closest match in the feasible palette. And I guess another thing to note is that the SVG, you have to ensure that the shapes are not overlapping, because that's otherwise you would have shapes that kind of intersect each other in the mosaic, and that's not something that's feasible to fabricate. And sort of from there, users can also explore the available color palette and fine-tune the colors in their design. But what I really like about this interface is that we provide this interactive mode, which allows users to sort of build intuition on the color changing effects. So the left side of this window shows the mosaic decomposed into its constituent components. And these are knobs that the user can adjust. And the right side shows the effect that those rotations have on the mosaic's appearance. So you don't have to like go through the trouble of fabricating the mosaic to see what's going to happen. You can just kind of prototype it in the tool and see that, make sure that it has the effect that you want before fabricating it. And under the hood, it uses the physics model to ensure that the color changing effects are accurate. Cool. And like before, our system produces fabrication files that we can then laser cut in this case, with each file corresponding to a different layer in the mosaic. So if you've used a slicing tool for 3D printing before, it's kind of basically the same idea. So instead of sort of slicing for the filament, we're slicing for stacked cellophane layers. So the process of fabricating these mosaics is just loading the layers of cellophane one by one, based on whatever layer the system says you need to put in at a time. And then you like run the laser cutter, peel away the layer, and then you repeat. So one thing to note is that during this laser cutting process, the mosaic holds together because the heat of the laser not only serves to sort of like cut out the shapes, but it also lightly welds them to the layer beneath. And I think most importantly, this was done with a completely unmodified laser cutter. So you can make one of these mosaics today with a standard sort of laser cutting machine. You can go to one of the the design studio that Ticha showed me, and just like buy a roll of cellophane from the craft store. Great, so we envisioned a few possible applications of mosaics you can make with our system. So this is a pair of fun glasses showing all 8 configurations. I'll just let it run through. Okay, cool. And I've also had the privilege of presenting polygons at the MIT Museum, and this is like, these are the glasses on the MIT Museum director. Yeah, and I think they broke after. Great, so this is a responsive display that we incorporated into a sliding glass door. So the idea is that when the person slides one side of the door open, it shows a message reminding them to close it. And we also made this tangible sort of physical data visualization, which shows how COVID hotspots changed between July and August 2021. Yeah, so this, you can actually, this is maybe a kind of a demonstration of how this project was made during the pandemic era, where this kind of visualization was more useful. Great. And we can also take advantage of existing mechanisms and objects. So this is a mechanical clock design that uses the rotational mechanisms of a clock to create these color changing effects on the design, the base. And again, what's encouraging is that even users with no prior knowledge of polarized light mosaics or birefringent materials were able to use our tool to design sort of valid fabricatable mosaics. And these are just like the variety of designs that users came up with in the user study that we ran. And we also open source the tool. So I'm hoping that in doing this, we can kind of grow this community of modern polarized light mosaics and kind of keep this art form alive. Yeah. So whereas Polygon uses a material with unique optical properties, FabObscura demonstrates how we can use perceptual tricks to give normal materials special optical properties. All right, so in the 19th century, long before cinematography or film even existed, engineers and craftsmen developed a range of these really interesting analog techniques for depicting motion. And one such technique that was developed in the late 1800s, that's still being used today to some extent, is barrier grid animation. So the basic principle behind barrier grid animations is that you have an interlaced image that encodes many strips of animation frames and a striped barrier mask. And these two layers are precisely constructed such that when you place the barrier over the interlaced image and move it along the interlacing direction, it plays the animation. So in this case, we interlace along the x-axis, and horizontal movement advances the animation. And of course, if you slide the barrier back and forth, it's like the same as playing the animation forward or backwards. So what's really cool is that this same principle actually works on a range of interactions. So we have sliding, as we saw before. And then we have these, what I call view-dependent effects. This is really similar to sort of like the lenticular prints, where it's an application of sliding animations where instead of kind of putting the barrier on top of the interlace image, you offset them and then fuse them into one structure. And that offset causes it to appear different depending on the angle that you look at the animation. And then we have these rotations, which applies the interlacing on a polar coordinate space. So, despite their simple construction, barrier grid animations actually have a lot of potential to function as analog interfaces. But you may notice that these animations actually have a pretty restricted visual vocabulary. So even though you can design, a variety of animations and interactions, existing processes only support sort of straight line barrier patterns. Like the process by which people construct these animations is very entrenched. And that hasn't changed since like the 1800s. So what we were interested in was how can we raise the expressive ceiling of these animations by introducing new kinds of barrier geometries, and how do we do this in kind of a systematic and scalable way? And you might be asking, why would we want to do this to start with? My argument is that barrier masks are often viewed as sort of undesirable aspects of the animation because, by design, they obscure the image that you really care about, which is the animation. And you can't avoid having a barrier in the barrier grid animation, so you might as well try to make them look nice. But it turns out that if you can make modifications to the barrier, it can improve the expressive qualities of the animation. So adding a simple curvature to this animation's barrier creates this effect of a vanishing point. So if we can instead consider barriers as part of the design space instead of something to be ignored, we can breathe new life into this old animation medium. Okay. So to understand how to raise the expressive ceiling of barrier grid animations, we have to first kind of understand them from first principles. So essentially, what we had to do was throw away existing sort of very procedural methods of constructing these animations and just think from first principles, what makes a barrier grid animation a barrier grid animation. So we do this by identifying these canonical properties that any valid barrier grid animation must satisfy. And just from looking at a bunch of these barrier grid animations, closely studying them, and also building them out ourselves, we found that this boils down to three key properties. There's seriality, which reveals animation frames in order, periodicity, which loops the animation, and discreteness, which ensures that at most one frame is fully visible at a time. So together, these properties provide this conceptual framework for the space of valid barrier grid patterns, and this applies to all types of barrier grid animations. So using these canonical properties, we can try to derive a general parameterization for barrier patterns. And the main insight is that our canonical properties essentially imply that we can represent a barrier as a repeated pattern unit. So for example, for a traditional sliding animation, each unit is just a straight line with a thickness equal to the interlacing resolution, or this is the width of each strip in the interlaced image. And then these units are stacked along the axis of motion, so in this case, it's the y-axis. And then when you fill in the barrier later, the transparency distribution corresponds to the number of frames in the animation. So if you have an n-frame animation, the barrier alternates between a single transparent stripe and n-1 opaque stripes. Okay, so what makes a pattern valid? So note that for a pattern to be valid, units cannot sort of cross or overlap each other. So if you consider a sliding animation that moves along the y-axis, this is the same as saying that each unit has to be uniquely identifiable at any x position. So any vertical line that passes through the barrier intersects each unit exactly once. But this is actually interesting because it's the same as passing the vertical line test in mathematics, which you may recall is a test to determine whether a curve represents a valid function. And what this implies is that we can actually reduce the space of valid barrier grid animations to the space of valid mathematical functions, which is really exciting because previously we thought that barriers could only be made with this like straight lines, but the space of mathematical functions is effectively infinite. So what does this mean? For traditional animations, this function is a constant. But now we can parameterize the barrier with any valid function, like this modulated triangle wave or this irregular looking sinusoidal product. And of course, right now, these constructions assume that we're just moving along the y-axis. But to support other directions of motion, all we have to do is just apply a rotation to the pattern, and it all still works. And again, these examples assume that the functions are in the Cartesian coordinate space. But this applies to polar functions as well. So in this case, each radial line in the pattern follows a path defined by a function f, which controls the local turning angle based on how far it is from the center. And as you move outward, f determines how much the line bends at each step. So when f is 0, you get the straight lines. But if you set it to a non-zero constant, it starts to sort of curve and spiral outwards towards the center. So to summarize, we can parameterize a barrier with 3 properties: its unit function, which is the shape of each unit, the thickness of the units, which is like the animation resolution or the spacing between the units, and the direction of motion. So based on this design space and this parameterization, we can now prototype a computational design tool for authoring and interacting with these animations from our parameterization. And what's nice is that since the parameterization works with all animation types, users can just move between different variants with low friction without having to sort of like regenerate or remake their function based on the animations they want to create. So the other exciting thing is that because of the simplicity of barrier grid animations, we can easily print designs with standard 2D printers and use them for a range of applications. This is like a dynamic coaster. And the concept is that you can adjust it to complement the beverage that you want to drink. And then this is a jar design that animates as the user opens it. Okay. And again, like polygons, we can take advantage of sort of existing mechanisms and incorporate these objects to make analog dynamic displays. I think that like maybe the contrast isn't like super great on this projector, but basically it's a mouse running on a wheel. Okay, you might have to like squint a bit and like maybe like stand back to see this, but our parameterization can even support animations that did not exist before. So this design encodes multiple animations. Essentially, like what it's showing here is like there's a car rotating when you slide left and right, but if you slide up and down, it transforms into a motorcycle, and then you can rotate the motorcycle again by sliding left and right. And this is another nested animation that combines 2 different animation types. So we have a view-dependent effects, which animates the animal. Hopefully that's kind of visible. But we're also using a sliding mechanism to switch between animations. So this is like an interactive sign. And it says, beware of crocodiles. And this is just a bunch of different animations that I made. To summarize, Fablets here demonstrates how we can sort of raise the expressive ceiling of these barrier grid animations, which we previously thought were a lot more limited. And barrier grid animations, might be considered by some people to be a niche art form. But I think that by expanding what's possible with barrier grid animations, we might be able to expand what's possible with the barriers that exist on and around us. All right, so I'm nearing the end of my talk, and I just want to take a moment to talk about how I see my work going forward. And I'm kind of on, now that I'm thinking about jobs and things, people often ask me sort of like, oh, Ticha, what do you want to do for the next 10 years or 20 years or something? And as I was, trying to figure out the answers to that question, I think the thing I'm most excited about is this idea of building the next generation of expressive tools. And I have some opinions about this, and they're still maybe not fully baked, but maybe I'll share them and hopefully get some feedback and ideas from you all. And let's call them claims because they have yet to be rigorously proven. And claim one is maybe more about my engineering approach or engineering philosophy. And it is that I think that if you can combine divergent perspectives on the problem, you can create new solutions. And this is why I believe in the value of doing interdisciplinary research. So one of my favorite projects that I worked on in my PhD, which I didn't get a chance to talk about in detail in this presentation, is Kinecam, which is a camera that prints these animated photographs. And we presented this at SIGGRAPH in the art papers track back in 2022. And what I like about this project is that it applies the centuries-old barrier grid animation technique, which you saw from before, with these widely available modern technologies. So in this case, it was just a microcontroller and a camera module. And this produces something that was previously only possible in fiction. And I think that we can always count on interdisciplinary people to produce new things. And there's a growing number of them, but they're still pretty rare and don't really scale. So, in response to this, a lot of people end up building interdisciplinary teams, which is great, but that can also be a cause of friction because sometimes different people speak different languages and they have different approaches. And I believe that, maybe we can bridge this gap by engineering interdisciplinary tools. So these are tools that draw upon multiple areas of knowledge to create new solutions for problems. And my second claim is, I think the key to expressiveness is this idea of preserving idiosyncrasies. So my work in fabrication focuses on making physical objects more expressive without having to sacrifice sort of the non-digitalness of the materials that they're made from. But if we were to think outside of fabrication, with creative tools in general, I think that it's really important to preserve the idiosyncrasies of the creator. So for example, I'm an artist. I do a lot of painting, like maybe too much painting. But despite all my experience with painting, I would say that I'm not the best at likenesses. So for example, here are some little paintings that I made recently. And these are the photos I used as reference. So they don't look exactly alike. Like the proportions are slightly off, the colors are a little bit shifted. And part of this, maybe you could argue it's a skill issue, but the other part is that there are decisions I make as an artist that is intrinsic to my personal style, my personal values. And I'm sure that if I asked everyone in this room to paint these images, you would all make something different. And I think one limitation of some of the new creative tools we're seeing is that they're operating at the wrong levels of abstraction. And I don't think the issue is that they're not doing enough. I think the problem is that they may be doing too much. So there's research that shows that instead of amplifying what makes us creative and unique, these tools are actually making us think the same or even talk the same. So going forward, I think it would be important to step back and think about how and where to preserve human agency in the design of these systems, because it's the human idiosyncrasies that yields divergent outcomes. So the last thought that I want to close on isn't really a research goal, but maybe more of a research value, which is the idea of making systems that make magic. So people in the past have told me that my research is like magic, which is always really flattering. But what I find most encouraging is that it's magic that empowers people to make things that they can't easily make on their own. And I think we live in this really exciting moment in time where technology is evolving like so fast. Like it's evolving much faster than like what we really know what to do with it. And you know, on the flip side, I think there's a lot of anxiety around whether these new tools diminish human value. Like if you have a tool that makes art, does that eliminate the need for artists? If you have a tool that makes code, does that eliminate the need for computer scientists? And, you know, I would hope not. But I think that, you know, thinking about the human factors in systems building has become more important than ever. And with all these developments in sort of machine intelligence, I think we're in a better position to answer challenging questions about human creativity. So as researchers and technologists, we have the power to distill all these complex processes into usable systems that enable new expressions, like not just for the sake of building something magical, but also for the end goal of empowering people. Because if we can shape our systems, then we can shape the tools we use. And if we can shape the tools we use, then we can shape the world. Thank you.
You have time for a couple of questions. I ask something annoyingly technical. In the barrier project, how did you choose which functions to use?
This is mostly something that I did through experimentation. I think that, you know, maybe like not providing template functions or something like is maybe like a usability issue that could be improved in the way that the system is built. But basically like I tried to input like different kinds of like sign functions and different things that just like it's purely experimental. Yeah.
But there's also a space of expressiveness there
Yes.
encoded within the design pattern.
Yes. Yeah.
Okay, and then do you think it's possible to like provide a computational objective on which function you should use? Like,
I think that.
And you know.
Yeah.
So you think, okay,
No, I agree. I think that would be an interesting way to make the tool like more functional and rich, because I agree that like, you know, right now, the way that we're interacting with the tool is like, okay, you kind of have to assume that the user has like some mathematical maturity to know that it's like, okay, if I have a sine wave, then we kind of look like this.
Yeah.
And I think that it would be really interesting to kind of extend it to maybe analyze a video, and based on like the way that the video moves, it can maybe like infer some sort of function that would like fit it well. Yeah.
Thanks.
This is more of a philosophical question, but you talk about, you know, raising the ceiling of what these tools can do, you know, or expressiveness, right? You know, but I mean, there's only words, or maybe tell me if I'm wrong, but it feels like, well, because you're constrained by some fabrication techniques, right?
Yeah.
Like in practice, oftentimes when we're building these design tools, we want to have some restrictions.
I agree. Yeah. Which is, I think this is also something that I'm trying to like hash out, because you can't, you know, especially when you're working with the physical world, there are like so many different constraints that you need to consider. I wonder if there is, because I know that there is also like some really interesting like literature and work about how like working with constraints can actually be very beneficial to creativity.
Exactly. Yeah.
So I wonder if there's a way to sort of leverage that in the design of these systems, but I still need to bake those ideas.
Right,
But that's
right.
a great point. Yeah.
Yeah, it's interesting because like often like when you, the constraints, exactly, the constraints are empowering, right? Like you don't
Yeah.
have to focus on specific aspects of
Yes.
your design.
Yeah.
Let's thank our speaker one more time.